Okay, so this just shows us as A, which is Z plus N, the mass number. As the mass number increases, the binding energy increases, but certainly not linearly, right? Okay, so that's great. Now, maybe what we should talk about, instead of just talking about the binding energy, maybe we should talk about the binding energy divided by A, So like 29 divided by 6, 105 divided by 14. Maybe we can learn something if we do that, okay? So we're going to look at just the binding energy divided by A. Where again, A is the number of protons plus the number of neutrons, okay? So this is just the energy that's required to remove one single nucleon, right? Okay. All right. So let's make a graph, okay, of how much energy is required to remove just one proton or just one neutron. So there's the graph. So it's the binding energy per nucleon, right? And this is the mass number, the A. Okay? So what do you notice? Well, I mean, it's not really constant, right? I mean, look, it goes, rises, right? Then it's kind of constant, but not really. I mean, it kind of goes down, Wow, we got to explain that. Okay? All right. Let's see. Everything is less than like 9 or so MeV, right? Here's like 9 or something. So all of the B divided by A, they're all less than 9 MeV. It's a lot. It's a lot of energy compared to atomic physics to remove an electron. Okay, now let's expand this graph. So we'll just look at this part. You notice it goes up, down, you know what I mean? So these guys here, they have, there's a lot of binding energy per nucleon. So this is pretty stable, right? This is super stable, much more stable than this, because this doesn't take as much energy to remove a nucleon. This takes a lot of energy to remove a nucleon. So this is super stable, that's super stable, that's super stable. Why? Well, we got to explain that too, all right? We got to explain that. All right, these peaks at A equals 4, A equals 12, A equals 16. We got to explain that, okay? Okay, now again, if you want to be super stable, you should have a large binding energy, right? A large binding energy, because that means it takes a lot of energy to break apart that nucleon, Okay. So which isotopes have the largest binding energy per nucleon? Which isotopes have the largest B divided by A? So look at that. Which ones have the largest? Well, looks like this guy and nickel and iron, huh? These are the ones that have the largest B over A. Okay? So those are the ones that are the most strongly or tightly bound. And we got to explain that when we talk about our model of the nucleus. Okay, awesome. I've got a lot of work. All right, now look here. So remember, in order to be a stable nucleus, which is what you want, right? Well, what they want, you want to have a large B divided by A. So this does not have a large B over A, so it's not going to be real stable. So in order to get these guys to be more and more stable, what do you have to do? Or what has to happen, maybe I should say that. What has to happen to these to get a larger and larger B over A? Well, they got to combine, right? They got to combine, because this only has, A equals 2. This has A equals 6. You get the larger and larger A, you get more and more stability, right? So, right? So if you can combine these guys somehow to get a larger A, more protons and neutrons, they would have a larger B over A, they'd be more stable. Well, that actually happens, and it's called fusion. What does it mean when you get your vertebrae and your back fused together? They're combined, right? Okay, so in order to become more and more stable, we can use what's called nuclear fusion to combine these so they get up there. All right. Now, how about over here? Here you have A equals 238, 197, 160. What do these have to do in order to get larger and larger B over A? What do you notice about their A's? 238, you know, nickel 62. So what do they have to do? Do they want to combine and get more protons and neutrons? No! They want to get rid of some, right? They have too many, right? Too many here. You want to get a smaller number. So that's called fission. So fission is when you don't combine, you break it up. Okay, you break up the nucleus. All right. Now, iron 56 or nickel 62, they have the maximum binding energy per nucleon. So are they going to undergo fission or fusion? No, because they're at the top. All right, they're at the top. And that's actually incredibly important in astronomy, believe it or not. So let's talk about astronomy for a minute, okay? All right, how do you form a star, or how are stars formed? Stars are formed from dense clouds of gas. So here, let's just say this is just incredibly, it's not supposed to be spherical. Don't think of this as spherical, all right? Just this giant cloud of gas. Now it's gas, right? Like most likely hydrogen. Well, hydrogen has mass, so just think of this, tons of hydrogen, particles, molecules or whatnot, atoms. Well, they have mass, so they attract each other due to gravity, correct? So what is this thing going to do? It's going to contract, right? A gigantic cloud of gas is going to contract because of gravity. Let's see, do I have a picture of that? No, I don't have a picture. Okay, now, so what happens when you have this incredibly gigantic cloud of gas? It collapses. Very good. Now, so what's happening to the potential energy of these hydrogen atoms relative to the center of the cloud? The potential energy is getting smaller and smaller. So what happens to the kinetic energy of these hydrogen atoms and molecules? It's getting faster and faster. So what happens when all these hydrogen atoms are starting to collide? Well, what happens when you have things that collide? Remember I showed you that demonstration in Physics 105? I had the two solid spheres, and they collided, and I put a piece of paper in between, and it burned a hole because the kinetic energy was converted to thermal energy, right? And the thermal energy burned a hole in that paper. So you're going to have this, so it's going to get hot, right? The center of the star is going to get hot. Now, when the center of the star gets hot enough, fusion begins. Nuclear fusion begins at the center of the star. Okay, now, this is kind of awesome. Let's talk about it. So what do you have in a star? Primarily hydrogen. So let's do it. So what happens, you have proton plus proton plus proton plus proton. Now remember, protons are positive. They repel each other. But when you have these incredibly high temperatures, like millions of degrees, they're going so fast that they actually combine, right? They combine. Nuclear fusion, they combine and they make helium. And a whole bunch of energy is given off when that happens. Okay? All right, so that's step one. So for a really, really big star, this is step one, right? The protons combine to make helium. By the way, what's helium? It's helium-4. So it's helium-4. Helium-4 is 2 protons and 2 neutrons. So 2 of these protons become neutrons. Okay? So after that goes on for a while, this is another way to write this is like this. 4H goes to He plus energy. Because we're just talking about the nucleus, right? And what's the nucleus of hydrogen? Proton, you know. Okay, so this is the same thing. So eventually, all of the hydrogen is going to be fused into helium. Now, what do we care? Remember, the star is collapsing because of gravity. Then, when it gets hot enough, fusion begins. When fusion begins, there's outward forces. So actually, the star becomes stable because the outward forces balance the inward gravitational forces. So the star becomes stable. Okay, now, so this is going to go on for, billions of years or who knows what. But eventually, the hydrogen is all going to be converted to helium. Well, when the hydrogen is all converted into helium, there's no more fusion. So what's the star going to do? Well, there's no more outward forces, right? So it's going to collapse. So it's going to get hotter again. And then, for a large enough star, then the helium starts to fuse to make carbon. Eventually, the helium's going to be all gone. Then the carbon fuses and blah, 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 blah. It just keeps going for a very, very massive star. Okay, so let's see. Oh, I don't want to ask that right now. Well, I guess you didn't see that. Oh, man. I kind of lost my place a little bit. Okay, that's okay. Don't worry. So here's a stable star. Okay, so fusion has begun, and you have the gravity forces compressing the star, fusion pushing out, so it's stable. So here's fusion. 4 protons or 4 hydrogens goes to helium plus other stuff. Now, as I said, this is going to keep going through different stages, right? Different stages. So you're going to have, hydrogen, right? Helium, carbon, oxygen, neon, magnesium, silicon, and eventually you're going to get this iron core. Iron core. By the way, stars make elements, right? Right? I mean, the star made the helium, the carbon, the oxygen, the neon, the magnesium, the silicon, and the iron. The star made it. It was made in the center of the star. Okay, now, here's the question. What happens when it gets to iron? What did we learn? Does iron fuse or fission? Not at all. So, if you get an iron core, it's not going to have any fusion reactions. So therefore, guess what? There are not going to be any forces to stop the contraction of the star. What does that mean? It means the star is going to collapse. If it's a big enough star, well, it's going to collapse. And there's going to be a supernova explosion, and you're going to get a black hole or a neutron star. So look, this is based on nuclear physics, this whole thing. Why doesn't the iron fuse? It doesn't fuse because it already has the maximum B divided by A. So it's incredible, right? It's incredible. Now, let's go back to the questions I forgot. All right, you didn't see the answer, right? Okay, here's a question. So this is the 4 hydrogen combines the helium plus energy. 4 protons forms helium plus energy. Why does fusion of hydrogen release energy? So this is the same thing. So why is there energy released? Why isn't it required? Why is it released? Here's my super awesome hint. E equals mc squared. So pause your video, please, and figure this one out. And this is a concept we're going to talk a lot about. We already did in the relativity chapter. How can energy be released? Okay, what's the answer? Look at, if energy is released, okay, here you have 4 hydrogen goes to helium plus energy. And we know that energy is mc squared. Where does energy come from? Well, the mass of this has to be greater than the mass of that, right? Because the missing mass becomes energy equals mc squared. So, what's the right answer? The right answer is 2. The mass of the helium nucleus is smaller than the mass of the 4 protons. All right? This has a higher mass than that. Where did the missing mass go? It became energy. So that's an incredibly important concept. Make sure you understand it. Okay. All right. Now, okay, let's see. I don't want to bother with that. Okay. Okay. All right, let's talk more about the nucleus. So here's this nucleus. Protons and neutrons, and they're tightly bound. You know, they're really close to one another, right? Now, what do protons do to other protons? What do we learn with electricity? They repel each other. What do neutrons do to protons, or what do neutrons do to neutrons? What did we learn with electricity? They don't do anything, right? Because they're neutral, they have no charge, so there's no electrical repulsion. Okay, so let's just focus on the protons. Protons are repelling each other. So how can you have this tightly bound nucleus when the protons are repelling each other? How does it work? What has to happen? Well, I mean, there has to be another force, right? If the only thing that was important is electricity, this thing wouldn't exist, right? It wouldn't be stable, okay? And gravity is nothing. It's absolutely nothing. We don't care about gravity. So there has to be another force. And it's called, guess what? It's called the nuclear strong force. The nuclear strong force. Pretty good name, right? Not very creative, but it's very descriptive, yeah? And what's interesting about the nuclear strong force, protons and neutrons carry this nuclear strong force, and it's attractive, okay? So a neutron is attracted to the neutron is attracted to the proton. Now here's an interesting one, right? So this is the strong force. So the nuclear strong force is much, much stronger than electrical repulsion, right? So for a proton and a proton, you get strong attraction, but you still have electrical repulsion, so this is the repulsion, okay? Let's read it. So the attractive strong force is the same for any two nucleons, right? See how the magnitudes are the same? However, two protons also experience a smaller electric repulsion, right? Okay. So that is why neutrons are stable, because there's this incredibly strong nuclear force that overcomes the repulsion and holds them all together, okay? Holds them all together. And it doesn't depend on the charge, right? The neutrons have it, the protons have it. Some people call it, it has a super, super short range. So it's strong, like the diameter of a nucleus, and then after the diameter of a nucleus, it goes like almost to zero. So what's an analogy? Like Velcro, right? Like Velcro, if they're not touching, they're not strong, right? Or glue or something like that. So some people call it nuclear glue, okay? Now, we're going to answer one of our questions that we asked earlier. Why are the stable isotopes, why do they want more neutrons than protons? Well, answer the question. You should be able to answer that right now. Well, remember, what do neutrons do? Neutrons they carry this nuclear strong force, right? So the more neutrons you have, the more strong force you have, so the more stable the nucleus, okay? There you go, all right? Isn't that great? So neutrons add stability because neutrons carry that nuclear strong force. Awesome. Okay, now let's completely switch gears. Let's talk about radioactivity. Radioactivity. Okay, what is radioactivity? It's spontaneous decay of the nucleus. So basically the nucleus has too much energy and it's not happy and wants to get rid of some of the energy, right? That's close enough, all right? But it's spontaneous. What does that mean? That means if you had a single nucleus, you have no way of knowing when or even if it's going to decay. It's a random process. If you have a large number of radioactive nuclei, you can say, you can say a certain number will decay, but you have no idea saying, oh, that one will, that one will, that one will, that one will. It's spontaneous, it's random. And again, this is nuclear physics, right? So it's decay of the nucleus. So look at, what did I just say again? I said you can never say which one is going to decay, but if they have a large number, you can say, you know, half of them will, half of them won't. What's that? That's probability. Where have you heard that? Quantum physics, right? Quantum physics, probability. Oops. Oh, man. Okay, so this is all based on probability. The whole radioactive decay is based on probability. Okay, so as I said, energy is released, right? And so it goes from a high state, a high unstable state, to a low stable state. And it's called ionizing radiation. So high energy, so it's dangerous, okay? What does it mean to ionize? It means like get rid of electrons, right? You know, you talk about ionizing the atom. And so there's way more enough energy to kick out all of the electrons in an atom. So what does it do? So it can ionize atoms. It can break molecular bonds. You know, that's why it's dangerous. It can break molecular bonds. There you go, all right? Like radiation from like microwaves and all that, really small energy, not a big deal, you know? Visible light, not a big deal. But this ionizing radiation where you're breaking molecular bonds, that can be dangerous. We'll talk about that later. Now, there are three main types of radioactivity. Okay, three main types. The first one is called alpha. So alpha. And what's an alpha? So an alpha particle, so this is what's getting emitted, right? So an alpha particle is a helium-4 nucleus, right? So in other words, you have this radioactive isotope, and it's too much energy, it's unstable, so it spits out an alpha particle. So it's spitting out a helium-4 nucleus. What's a helium-4 nucleus? So this is a nice way to write it, by the way. I mean, sometimes we just write like this, right? Helium-4. Now, helium means 2 protons. Since it's 4, 2 neutrons. Okay, but let's say you didn't have all this stuff memorized, you know, 2 protons in helium, 1 proton in hydrogen. Then you just write it like this. If you just write it like this, helium-4, 2, then this is the number of protons. This is the number of protons plus neutrons. We're going to see that this is really a nice way to write it. All right, so in alpha decay, you're spitting out this helium nucleus. All right, the second most common form of radioactivity, okay, what's after alpha? Beta, all right? Now it turns out there's beta plus or minus. What's a beta particle? So that means they have a radioactive nucleus, has too much energy, it's unstable, so it spits out a beta. It can spit out a positive beta or a negative beta. What's a beta? It's an electron, okay? So a beta particle is just an electron, or if it's positive, it's a positron, a positively charged electron. Okay, the third one, what's after? So alpha, beta, what's next? Gamma. So the third type is gamma. A gamma is just a high energy photon. Remember, you have this nucleus has too much energy. It wants to get rid of energy. So the third way you can do that is just shoot out a photon, a high energy photon. That's called gamma radiation. Now, obviously, they're completely different, right? I mean, this has no mass. This has a tiny bit of mass. This is like the Mack truck, right? I mean, right? And you know, this is no charge. This is positive charge or negative charge, and this is going to be positive because it's a nucleus. So they're very, very different. And if you ever use radioactivity, which a lot of people do for research or whatnot, you have to know how to treat them differently because they have different hazards. So here, so look. So this is some radioactive source, so it spits out an alpha, or a whole bunch of alphas. A piece of paper can stop an alpha particle. That's nice, right? However, the beta goes right through, the beta goes right through the piece of paper, but it's stopped by a sheet of aluminum. But what does a gamma do? The high energy gammas, they go right through the paper and the aluminum, and they're stopped by a big sheet of lead, thick sheet of lead. So obviously, if you're working with gammas in your lab, you've got to be really careful, right? You have to have really good shielding, right? Because you don't want to get irradiated by the gammas. Betas, you'll need aluminum. Alpha is just paper. Now, there's more to it than that, obviously, but I'm just showing you the very different, very, very different penetrating ability, right? Penetrating ability. So, like in a hospital where they use gamma rays to kill cancer, well, they have to have that room with the machine that emits the gammas. The room has to be surrounded by thick lead or steel or something like that, because obviously you don't want to irradiate, people around outside the room, right? And so this is incredibly important in the real world. Okay, let's get into the details. Oh yeah, one more thing, sorry. F equals ma, right? So A equals F over m. So this is a lead block. It emits alphas, betas, and gammas. This is a magnet. What does a magnet do? Remember we learned that when we talked about magnetism? We learned this equation. Well, how about just this? Or F QVB sine, QVB sine theta, right? Okay, so we learned that if you have a charged particle in a magnetic field, there's a magnetic force on it. Well, okay, so look at, here's a gamma. It doesn't get deflected at all. Why? Well, because what's the charge of a gamma? 0, so there's no magnetic force. Okay, here's a beta, let's say it's a negative one. Now, so it's going to be bent. And then what's the mass of an electron? Hardly anything. So it's a big, big acceleration, right? Big acceleration. Now here's the Mack truck, the alpha. Remember, if this is negative, this is positive, so it's going to be bent the opposite direction. And since it has a larger and larger mass than the beta, the acceleration is going to be smaller, so it's not accelerated as much as the beta. Okay. All right. So let's go into detail now. Okay, let's talk about alpha first. Actually, let's quit. Yeah, let's quit.